During this video, I will navigate through different aspects, very important aspects of the urinary system, like how sodium and water is reabsorbed, how glucose is reabsorbed, the hormones that affect or influence the actions of the nephrons, and also the renal plasma clearance. To explain the reabsorption of water and sodium, we have to refer where this reabsorption takes place. And this reabsorption takes place mainly in the nephrons and specifically in the nephron tubes. Now, let's remember what is reabsorption or what is considered reabsorption. Reabsorption is considered about the movement of the molecule from a tube, in this case are the nephron tubes, back into the capillaries nearby. The capillaries nearby are represented by the peritubular capillaries or the vasa recta. In general, when we refer to the capillaries, we refer that molecule goes back to the bloodstream. In other words, remain in our body. Now, we mentioned before that we filtrate an average of 180 liters of blood per day. That is filtrated, considering that the largest amount of blood is made by plasma, and plasma is made, 92% of plasma is water, we can assume that 180 liters of water are filtrated per day. However, we urinate only 1 to 2 liters that is excreted in the urine, with the urine. In other words, 99% of that 180 liters filtrate are reabsorbed back in the peritubular capillaries. In other words, remain in our organism. Now, this amount of urine that we eliminate or we excrete increase when we are well hydrated, but also decrease if we are not well hydrated or we are dehydrated. Now, considering that we can be dehydrated, the minimum amount of urine that we can excrete per day, enough to eliminate the waste material that need to be eliminated, and the only way to excrete it is through the urine, is a minimum of 400 milliliters, roughly is half a liter. So that one is the minimum amount of urine that we can produce. Below that number, our entire physiology is affected. Now, from that 99% that is reabsorbed back in the peritubular capillaries, and I'm talking about specifically about water, 85% is reabsorbed in the proximal convoluted tubes and descending loop of Henle. Just a little bit is reabsorbed in the collecting tube. Now, I'm going to explain in more detail how water is reabsorbed. We reabsorb water in different steps during the urinary system, and specifically during the transition of the filtrate through the different tubes of the nephrons. Now, 65% of the water is reabsorbed in the proximal convoluted tube. It's a large amount. 65% of the water filtrated in the capsule is reabsorbed in the proximal convoluted tube, and is still too much filtrate from other molecules. Now, an additional 20% more of water is reabsorbed through the descending loop of the loop of Henle. Now, at that point, from the loop of Henle, jump into the medulla, the renal medulla, and from the renal medulla goes back into the capillaries around the loop of Henle that are called vasa recta capillaries. And this process is totally unregulated, is not affected by the action of any hormone, and happen continuously. The 65% reabsorb in the proximal convoluted tube, and the second one, that is the 20% additional at the loop of Henle, is unregulated. Now, the reason why water moves from one area to the other one is following the higher concentration of solutes, but is not affected by any hormone. The final 15% of water, that is an average of 27 liters, is absorbed or reabsorbed later in the collecting tube, but this action is under the influence of the ADH hormone, antidiuretic hormone. Now, it's important to keep in consideration that the fluid that is entering into the loop of Henle after the proximal convoluted tube is isotonic to the extracellular fluid, so is basically imbalanced. And later in this video, we will learn how that loop of Henle is acting to reabsorb that 20% additional of water. So, be familiar with the three basic physiological movements that take place in the nephrons. That the first one is filtration. Filtration happens or is driven by hydrostatic pressure, when all the possible molecules are filtrated from the glomerulus into the capsule. And remember that just the certain molecules remain in that glomerulus, like the blood cells and the proteins. Ideally, they remain in the glomerulus. However, all the other possible molecules are filtrated into the capsule. From the capsule, they pass into the tubes, the proximal, the loop of Henle, the distal, and the collecting tube. And during that tubes, any of those, without a specific one right now, they take place the other two actions, either reabsorption or secretion. Keep in mind that in reabsorption, the molecules move from the tube back into the capillaries nearby. In this case, could be the peritubular capillaries or the vasa recta. And in secretion, the molecules move in the opposite direction. They move from the capillary nearby, one of the three that I mentioned before, back into the tubes to be excreted in the urine. So, after the molecules were filtrated in the capsule, pass into the proximal convoluted tube. The function of this proximal convoluted tube is only reabsorption. There is no other action that takes place in the proximal convoluted tube. Now we mention what reabsorption means, how it's happening, and it's important for you to emphasize, and please write this down, that the reabsorption at the proximal convoluted tube of the molecule is unregulated. And when I mention that it's unregulated, there is not an influence of hormones that affect this reabsorption. The reabsorption takes place by different mechanisms that could be passive or active movement through the cell membrane, but certainly there is no one hormone that affects this reabsorption. Now, the osmolarity of the filtrate after is filtrated in the capsule and is reaching into the proximal convoluted tube, the filtrate osmolarity is isotonic. Remember, the isotonicity is in our organism is an average of 300 milliosmoles. Now, in this proximal convoluted tube, the sodium, and it's important for you to understand the movement of the molecules, because certain molecules are the ones that are driven the movement of water, and these molecules are for example glucose or sodium or potassium or calcium or chloride. This molecule, and I want to emphasize the movement of sodium. Sodium is transported and is actively transported, active transportation from the tube into the peritubular capillary. And this movement is the one that set a concentration gradient that drives osmosis, as I mentioned before. Now, sodium is moved from the proximal convoluted tube into the peritubular capillary by active transportation. Yes, is moved by using energy. Now, when sodium in the peritubular capillaries, the sodium concentration in the peritubular capillaries increase, that one is the reason why water will follow that high concentration of sodium into the peritubular capillaries. And in this way, not only we reabsorb sodium, we reabsorb water as well. The same scenario happened with other molecules that I mentioned before, like calcium or glucose. Now, in terms of chloride, I mentioned in the previous video that chloride moves in the same direction like sodium. Is like husband and wife. Sodium is the one that takes the action, is the one that set the direction, and chloride will follow no matter what, because there are opposites attract, and is how these two molecules move together. Now, as I mentioned before, sodium chloride move first and water then follow that high concentration of these two molecules. Now, the salt and water diffuses into the peritubular capillaries. Why I'm saying that? Because remember, when we move molecules from one compartment to other compartment, our physiology use always the interstitial fluid. So molecules move from the tube to the interstitial fluid, and from the interstitial fluid jump into the peritubular capillaries. In this graphic, you can observe that after the filtration that takes place in the renal capsule, those molecules, and we are talking about water and sodium specifically, right? That molecules move into the proximal convoluted tube, and right there, the one that set the concentration are the movement of sodium and chloride. So sodium is transported actively from the proximal convoluted tube to the interstitial fluid, and from there goes back into the peritubular capillary. So in that way, we retain sodium in our system. When sodium moves in one direction, chloride follow that movement of sodium, and chloride move passively. These two molecules set a concentration gradient that drives the movement of water, so water will follow this concentration gradient, and in this way we reabsorb sodium, chloride, and water. Now, we mentioned that the filtrate was isotonic, and after we reabsorb these molecules, the filtrate that remain in the proximal convoluted tube is still isotonic. After the filtrate pass the proximal convoluted tube, where the maximum reabsorption and regulated reabsorption take place, the filtrate reach the loop of Henle. As you know, the loop of Henle is composed by two limbs. The first one, that is descending, goes from the proximal convoluted tube deep in the medulla, and from the deep of the medulla, emerging to the cortex, produce the ascending limb that is finishing at the distal convoluted tube. Now, it's important to know that right here there is an additional reabsorption of water of average 20% from the 99% that was reabsorbed at the beginning. So 65% was already reabsorbed in the proximal convoluted tube. Now we need to reabsorb additional 20% of water. How is happening? Well, I mentioned before that in the proximal convoluted tube, water is reabsorbed following the high concentration of other molecules. Sometimes it's sodium, sometimes it's glucose, but certainly it's following the higher concentration of those molecules that they were reabsorbed in the proximal convoluted tube, from the proximal convoluted tube to the peritubular capillaries nearby. In this case, water is following the same action, is following the higher concentration that is produced in some way, somehow. Now, let me explain a little bit because it's a little complicated. Now, how water is reabsorbed is following the system that is called countercurrent multiplier. Countercurrent multiplier. What's happening in the loop of Henle is when is produced the concentration of urine. Is the 100% concentration of urine? No, but it's the largest concentration of urine because remember the product that left the proximal convoluted tube was isotonic with a large amount of water and still a large amount of molecules, especially sodium. Now, when the filtrate get into the proximal convoluted tube that is following the arrow, is at the top left, 300 milliosmoles. Try to ignore what happened in the descending loop. I make a sign that the first movement takes place in the ascending loop. In the ascending loop is where sodium and chloride is reabsorbed. Sodium is reabsorbed by the sodium-potassium pumps from the tube into the medulla. Chloride will follow this concentration of sodium. Now, why I said that the action takes place right here? When sodium moves into the medulla, the concentration of sodium into the medulla increase, and because of that, water will follow. Water will follow the concentration of sodium into the medulla after try to dilute the medulla. From the medulla, the water jump into the capillary nearby that is the vasa recta. Sodium also goes from the medulla into the vasa recta, but in different rate, because the function of the countercurrent multiplier and the vasa recta in combination of both produce a salty medulla. That medulla remains with a hypertonicity of sodium at all time and is the one that is accentuated by the reabsorption or the movement of sodium from the ascending limb into the medulla as well. And it's the reason why we need to use a pump, because the medulla is already salty and we need to move sodium from the ascending limb into that medulla. Now, following this action is the one that decreases the osmolarity from the deep of the medulla to the cortex, and you read that the osmolarity is decreasing from the deep of the medulla, like could be 1000 milliosmol to 800 to 600 to 100. So we decrease the concentration of that solute. That osmolarity is decreasing from the deep of the medulla to surface of the cortex, and I'm talking in the ascending limb. Now, simultaneously, what happened in the descending limb, and keep in mind that this action takes place after that, because the descending limb is only permeable to water. The ascending limb is only permeable to sodium chloride. Now, the descending limb is following that high concentration of the medulla. Because of that, water is moving from the tube to the medulla, increasing the osmolarity. Meanwhile, is getting into the deepness of the medulla. And you can read in that descending limb that the osmolarity from isotonic at the beginning of the descending limb is increasing to 6 to 8 to 1000 to the deepest of the medulla that can reach up to 1200 milliosmoles. So in this way we reabsorb water and sodium, but mainly water. Let me explain in more detail what happened at the ascending limb of the loop of Henle. This ascending limb is only permeable to sodium chloride and potassium. And what happened right there is the sodium is moved from the ascending limb into the interstitial space that represents the medulla and is moved using the sodium-potassium pump. Actively, that sodium-potassium pumps are using tons of energy to produce the action. Now, chloride will follow sodium just for the opposite electrical charge and is moved passively. However, potassium is moving in different direction because it's moving from the medulla into the tubes, into the filtrate. Now, that ascending limb is not permeable to water, so the high concentration of potassium that is concentrated now into the medulla cannot be compensated by this ascending limb because it's not permeable to water. There is not possible to have one aquaporins over there. Now, that tubular fluid entering the ascending loop of Henle becomes more hypotonic at the time more sodium is moved from the tube into the medulla. So that hypotonicity increase. Meanwhile, the filtrate is moving ascendingly into the loop of Henle from the deep of the medulla back in the cortex. Eventually, that sodium in the medulla will remain some in the medulla and some of them will go into the capillary nearby that is the vasa recta. That is used also to move water into the vasa recta, but I will talk in more detail about that later on. Now you have to know that the sodium that is moved from the ascending limb go into the medulla, and some of them will remain in the medulla, some of them will be moved into the vasa recta. What happens simultaneously in the descending loop of Henle? Remember that the tubular fluid that is entering the descending loop of Henle becomes more hypertonic as it descends into the medulla. As I mentioned before, is at the time is getting into the descending limb is isotonic, and at the time is descending into the medulla becomes more hypertonic. Now, that descending limb is only permeable to water, is not permeable to other molecules, and water is drawn out of the filtrate and into the interstitial fluid space that is the medulla, following and is driven by the high concentration of sodium chloride in the medulla. Now, eventually, later on, that water in the medulla will be picked up by the vasa recta capillaries. As I mentioned before, that vasa recta pick up all the 20% more reabsorption of water from the descending limb goes back into the vasa recta. Now, the amount of sodium that we move from the ascending limb into the medulla will go into the vasa recta partially. And the reason is because we need to keep that medulla salty. So as it descends, the fluid becomes more solute concentrated. What other important concept is related to um, the same topic is the countercurrent multiplication. Why is that? Because it's a positive feedback mechanism created between the two portions of the loop of Henle. In other words, more salt the ascending limb removes from the tube, more water is moved from the descending limb into the medulla, and the fluid inside the descending becomes saltier. Now, it's saltier because there is less amount of water in the descending limb, meanwhile goes deep in the medulla. So more water is reabsorbed. These two systems between the loop of Henle, where is reabsorbed water and sodium, is called countercurrent multiplier, but is complemented by the countercurrent exchange that take place between the medulla and the vasa recta. After I explain the specific mechanism that take place in the ascending limb and in the descending limb, I took the time to summarize over here the sequence of events that happen in the countercurrent multiplier mechanism. Now, the first step is the interstitial fluid is hypertonic. The interstitial fluid is the medulla. Is hypertonic because the sodium chloride that is pumped from the ascending limb into, into the medulla. Now, following that high concentration of the medulla, water leaves in the descending limb by osmosis. So the movement of water from the descending limb into the medulla is driven by that just by osmosis. Molecules move towards the higher concentration of solutes, and in this case, the higher concentration of solutes are in the medulla. Now, that situation makes the filtrate in the descending limb hypertonic going into the ascending limb. So, is in the descending limb become at the beginning is isotonic, and meanwhile is descending into the deepness of the medulla become more and more and more hypertonic. So more sodium chloride in the descending limb can now be pumped out into the interstitial fluid because the movement of water. Now, the greater concentration of the interstitial fluids draws more water from the descending limb, and is one trigger the other one. What happened in the action in the ascending limb trigger the action in the descending limb, and vice versa. So that scenario continue until the maximum sodium chloride concentration from the inner medulla is reached. At the end of the distal convoluted tube, the filtrate is hypotonic. And it's hypotonic because all the process as I mentioned before, and with that hypotonicity that become between 200 to 100 milliosmoles, that one is creating the best scenario to allow our system, our body, to reabsorb additional 15% more of water at the collecting tube, but this action takes place by the action of ADH. I invite you to follow the direction of the filtrate in this graphic. Let's start from the renal corpuscle. After the capsule receives the filtrate, that filtrate goes into the proximal convoluted tube. At the proximal convoluted tube, the maximum amount of reabsorption takes place, and still become the filtrate is isotonic with 300 milliosmoles. With this osmolarity, reach into the medulla in the loop of Henle with the descending limb and the ascending limb of the loop of Henle. In the descending limb that is only permeable to water, water is taken out, is moving out of the descending limb into the medulla following the higher concentration of that medulla. Meanwhile, the filtrate navigate into the descending limb become more and more and more hypertonic until they reach the deepness of the medulla. In the deepness of the medulla, that osmolarity reached the maximum amount that is an average 1200 milliosmol and is where the ascending limb takes place. Now, this osmolarity starts to decrease, meanwhile that filtrate navigate back into the cortex. Why? Because this ascending limb is only permeable to other molecules but not for water. So in that ascending limb, we take sodium and chloride out, inside the medulla. And because of that, that osmolarity from the 1200 is reduced, and until at the end of the ascending limb, that osmolarity becomes hypotonic. And this hypotonicity remains until that filtrate is dumped into the collecting tube. In the collecting tube, and because of that hypotonicity means that we still have additional amount of water, that hypotonicity become in reverse, become hyper and hyper and hyper. Meanwhile, this go into the deepness of the medulla again to reach the minor calyx. Why? Because in this collecting tube of the nephron is the action of the ADH that push water outside of the tube and get back into the capillaries nearby. And in this graphic, I try to explain the combination of the countercurrent multiplier that happen in the loop of Henle and the countercurrent exchange that happen between the medulla and the vasa recta capillaris, represented parallel to the loop of Henle. As I mentioned before, the vasa recta has a very important role in that famous countercurrent multiplier and countercurrent exchange. That vasa recta runs parallel to the loop of Henle, either the descending or the ascending limb. In fact, that vasa recta also have the descending limb and ascending limb as well. Now, the function of that vasa recta is concentrate the urine, but mainly maintain the hypertonicity of the renal medulla in the way that I mentioned before, because that vasa recta is the one that will take that 20% of water that move out of the descending limb into the medulla, will take the 20% back in the vasa recta. However, the amount of sodium that is taken or is moved out from the ascending limb into the medulla, not all of them will go back in the vasa recta. Some of them will remain in the medulla, and that one is one of the particular or characteristic of the renal medulla, that is more permeable to water than sodium chloride. Now, imagine that keeping the hypertonicity of the renal medulla is tremendously important, and this is the main function of the countercurrent exchange produced by the vasa recta. In the following slide, I apply an extra slide with extra information about the vasa recta for you to increase your knowledge, and has another element to analyze, and probably will help you to study this very difficult concept. Urea is a waste product produced by the cells after the protein metabolism, and certainly is a waste product need to be excreted. And the only way we have to excrete urea is through the urinary system. However, urea has another functions in the mechanism of the nephrons, because urea is helping or contribute to the countercurrent mechanism in the loop of, between the loop of Henle and the collecting tubes. That urea has an special characteristic that is helping to keep the necessary osmolarity in the loop of Henle, especially in the ascending loop of Henle, because that urea that is ready to be eliminated in the collecting tube eventually can move from the collecting tube into the ascending loop is if the action of the sodium potassium pumps is above the need of that ascending loop. If that one is the case, and in case too much sodium chloride was taken out of the ascending limb, urea will move from the collecting tube back into the ascending limb. Now, in other words, the urea function in the urine concentration is helping to set up the solute concentration gradient inside of the nephron tubes. In this scenario, I specifically mentioned the interaction of urea with the ascending limb, but also it can happen in other areas. Certainly, urea is 100% filtrated from the glomerulus into the capsule. From the capsule run into the proximal, is not reabsorbed at all, but eventually urea can be helping in keep the concentration gradient of these nephron tubes. We explained in several chapters before the action of the ADH and the collecting tubes. Now, imagine that filtrate that is getting into the collecting tube has a very low osmolarity, is hypotonic, average 200 to 100 milliosmoles. And this one is the last chance our organism has to reabsorb extra 15% of water, or more, or less. It depends with the scenario. But certainly, if there is any kind of reabsorption of water at the collecting tube, it happens only under the action of the ADH. Now, simultaneously, this tube is totally impermeable to sodium chloride. By the action of ADH, the collecting tube's membrane increased the amount of aquaporins, because this is the action of the ADH. ADH is secreted according with the osmolarity. In other words, when the osmolarity of the plasma increase, the ADH is stimulated, secreted from the posterior pituitary, and the target are that cells in the collecting tube. What is the action of how the ADH is working? Is increasing the aquaporin in the aquaporins in the collecting duct of the nephrons, and in this way we can reabsorb extra 15% of water. Now, I want to mention that in case our body is dehydrated, our body has a system to inhibit the action of the ADH to don't reabsorb any molecule of water at the collecting tube. Now, in other words, increasing tonicity increase the ADH production, decreasing tonicity decrease or inhibit the ADH production. Obviously, this graphic represents the action of the ADH in the collecting duct membrane. That is obviously increasing the aquaporins. So that aquaporins can be embedded or removed. But certainly the only that can embed or remove the aquaporins is the action of ADH in this collecting duct membrane. And as you see in this graphic, from this amount from 0 aquaporins to the end, from 1 to A, B, C, and D, finish with 5 aquaporins. This graphic is really very powerful, and I invite you to navigate with me or by yourself, because it's very clear how the ADH can be stimulated to be secreted or decreased to be secreted. Now, the two scenarios are at the top, and I'm going to navigate on the left side where the patient is dehydrated. The patient can be dehydrated for different reasons, but the most common reason is because the patient has a low water intake. When there is a low water intake, the plasma osmolarity increase. Low water intake. That increased osmolarity is detected by the osmoreceptors in the hypothalamus. Now that hypothalamus informs the posterior pituitary to what? To secrete or not. We are in hypertonicity. So we need the increased secretion of ADH. ADH is secreted, and when it's secreted, the target of the ADH is in the kidneys, where the nephrons, where the collecting tube. And what happened over there? Increase the aquaporins, and in this way we reabsorb water that was ready to be excreted in the urine, but we reabsorb water in order to decrease the osmolarity. Now the osmoreceptors are informed about the scenario and the scenario change. On the right side of the slide, you have a different opposite scenario where we have high water intake. Obviously, within the limit that is beneficial for our physiology. But if we have high water intake, the plasma osmolarity decreases. Now, the osmoreceptors are informed that the plasma is hypotonic. In hypotonicity, the osmoreceptors inform the posterior pituitary to inhibit the secretion of ADH. Now, we know ADH, the target of the ADH is the kidneys. We know ADH, there is no water reabsorption at the collecting tube. In other words, we eliminate more urine and more water is excreted in urine. Is it fascinating, isn't it? I highly encourage you to play with this graphic that is talking about osmolarity increase or osmolarity decrease, and also play with the blood volume when blood volume increase or blood volume decrease, because one is related to osmolarity, the other one is related to um, to blood volume that decrease or increase, and what happened in the effect of this one in the urine, what happened with the urine volume, and what happened with the blood pressure. This graphic is really, really very powerful, and I invite everyone to play with the different scenarios that are presented over here. Now it's time to explain the reabsorption of glucose. Now, that glucose is easily filtrated from the glomerulus into the capsule, uh, and there is not a big deal over there. However, that glucose should be 100% reabsorbed in the proximal convoluted tube. In other words, we don't have, or we shouldn't have, one molecule of glucose in the urine that we excrete. In other words, this glucose should be reabsorbed 100% in the proximal convoluted tube. How is reabsorbed is through different mechanisms. Some of them are by passive transportation, some of them are by active transportation. But certainly glucose is ideally 100% reabsorbed in the proximal convoluted tube. Now, what happens when there are different scenarios, or either because we consume or intake a really high dose of carbohydrates or sweets or sweet things, or either because the patient doesn't produce insulin and that glucose cannot be absorbed by the cells, because without insulin we don't have the insulin tyrosine kinase system in place, and without that glucose cannot be absorbed. So either or the scenario, when we have high glucose concentration in the filtrate, ideally should be reabsorbed 100%, but in one of the two scenarios, that concentration can reach the 180 milligrams per deciliter. If that concentration is above 180 milligrams per deciliter, glucose cannot be reabsorbed completely in the proximal convoluted tube and will remain in the following tubes, either the loop of Henle or the distal convoluted tube, and also in the collecting tube. Now, this one is called the 180 milligrams per deciliter, is called the glucose threshold. That means above this concentration, glucose remain in the tubes. What happens with glucose remain in those tubes? If that glucose increased concentration remain in the loop of Henle, now the water in the loop of Henle won't leave the descending loop into the medulla, will remain, try to dilute down the high concentration of glucose inside the descending loop, and also will remain in the ascending loop. Now, this one is a condition that is flipping the function of the loop of Henle. That was countercurrent multiplier, reabsorb 20% more of the water in the filtrate. Now, this one doesn't happen. Because of that, the volume of urine increased, and this one produced a condition called polyuria. Polyuria is high volume of urine. When I mentioned that glucose remains in the urine and is found in the urine excreted, is called glucosuria. Now, these two conditions are the ones that trigger the other symptoms of diabetes, that is polydipsia, because if we urinate large amount of urine, in other words, we eliminate large amount of water, imagine that the patient can be dehydrated. If it is dehydrated, the osmoreceptors sense it, and one of the actions is trigger thirstiness, and the patient is intaking large amount of water to compensate, and this one is called polydipsia. There are the three signs of diabetes. Now, extra glucose in the blood also result in decreased water reabsorption and possible dehydration, as I mentioned before. This complex mechanism is important to take in place in order to understand that we need to keep that glucose levels in balance regardless if you are diabetes or not. But if you have one of these disorders, that that concentration of glucose inside the blood reach the threshold that is 180 milligrams per deciliter. And any single molecule has a threshold as well. I'm just mentioned the threshold, the glucose threshold. After we explain in more detail the function of the proximal convoluted tube and the loop of Henle, briefly, I would like to summarize the action of the function of the distal convoluted tube, because I mentioned at the beginning in the previous video which one is the function of the distal convoluted tube, that is produce secretion or reabsorption, but is regulated by hormones. So there are different actions that take place in that distal convoluted tube that could be secretion or reabsorption. And most of them are regulated by hormones. I try to summarize over here the hormones that are influence that distal convoluted tube. One of them is the aldosterone. You know very well that the aldosterone, where is secreted, and all that from different previous chapters and videos, but certainly aldosterone is secreted when the blood pressure drops or when there is a low sodium intake that produces also drop in blood pressure. Now, that scenario stimulates the secretion of aldosterone. What is the action of aldosterone? Is stimulate the sodium reabsorption. Water will follow. So aldosterone indirectly reabsorb water, and by doing so increase the blood volume and obviously increase the blood pressure. The other hormone that is related to this one is the angiotensin II, because angiotensin II stimulates the secretion of aldosterone and ADH. The action of aldosterone I just mentioned. The action of ADH I will mention after that, because it doesn't take action in the distal convoluted tube. Just a little bit, but not most of the time. The other hormone is the AMP, secreted by the atriums in the heart. This hormone stimulates the secretion of sodium, as by secretion of sodium, water will follow. When we reduce the blood volume, we decrease the blood pressure. So aldosterone increase the blood pressure, angiotensin II increase the blood pressure, AMP decrease the blood pressure. Now, I mentioned about the ADH because the action of the ADH is mainly in the distal convoluted tube, but not only. I don't want to complicate you, so keep focused. The ADH action is at the distal convoluted tube, and the ADH is secreted when the tonicity in the plasma increase, become hypertonic. And this one is the reason why the ADH is secreted. And the action of the ADH is reabsorption of water by increasing the aquaporins, stimulate the reabsorption of water at the collecting tube. And this action is, I want to emphasize, that is the only hormone that produces reabsorption of water directly and increasing the blood volume and increasing the blood pressure. Finally, is the time to talk about the renal plasma clearance. What is the definition of the renal clearance? Clearance is the ability of the kidneys to remove undesirable molecules from the blood plasma and excreting them in the urine. This one is what is the renal clearance. Now, keep in mind that the renal clearance is acquired by different actions, could be in combination of all of them or only one of them, are the three main movements that take place in the nephrons tube, in the nephrons itself, that is filtration, reabsorption, and secretion. Now, the process of clearance become or is starting with the filtration. Now, the reabsorption or secretion is the one that can affect that clearance. Why? Because the reabsorption is the returns of a certain substance back into our bloodstream. And if there is a reabsorption of that molecule, decrease the renal clearance. On the contrary, the secretion finish the process when substances are moved from the peritubular capillaries into the tubules, and this action increase the clearance. Now, remember the equation that I made in the first video of the urinary system when I wrote that filtration plus secretion minus reabsorption equal urine volume. Well, right now is the time to bring this concept back because the excretion rate is exactly producing the same formula, is filtration rate plus secretion rate minus reabsorption rate. That clearance is used to measure the glomerular filtration rate, and is that glomerular filtration rate that average is 125 milliliters per minute between the both kidneys is an indicator of the renal health. As I mentioned before, the renal clearance is defined as the removing of undesirable molecules from the plasma and excreted into the urine. And the only way that we can produce this clearance is in the kidneys, specifically in the nephrons. That's why the knowledge about the action of filtration, reabsorption, secretion, and excretion have to be very solid in your study. I mentioned before that the excretion rate is calculated by the filtration rate plus the secretion minus the reabsorption rate. Now, sometimes the labs are using different molecules to measure the glomerular filtration rate because it's the only way to measure the renal clearance, measuring the glomerular filtration rate. How we measure that glomerular filtration rate is using a molecule that have to be necessarily filtrated, sometimes reabsorbed, sometimes secreted, or sometimes never reabsorbed or never secreted. It depends with the molecule. One common molecule is used to measure the glomerular filtration rate is creatine, but another one is inulin. In the book, you read about inulin, and inulin is a molecule that is, for example, is injected through an IV, is injected in the bloodstream, and after a specific amount of time is measured in the urine. Now, because inulin is 100% filtrated, but is never reabsorbed and never is secreted into the tubes, the value of that inulin in the urine that we collect after that specific amount of time represent the glomerular filtration rate. Now, go back to the values of the glomerular filtration rate. Normal average glomerular filtration rate is around 125 milliliters per minute combined between the two kidneys. In other words, is the amount of that glomerular filtration rate between the two kidneys. Now, if the molecule is filtrated but is never removed from the tube by reabsorption and is never added into the tube by secretion, that molecule in urine after that specific amount of time represents the glomerular filtration rate. Now, another scenario, and please pay attention about that, if that a molecule can be reabsorbed, that glomerular, that clearance is below the glomerular filtration rate. And if that substance is filtrated and secreted, that clearance is above the glomerular filtration rate. The clearance of urea is below the glomerular filtration rate because is reabsorbed, can be reabsorbed at a certain time. So the goal is try to use a molecule that is never reabsorbed and never secreted. And in other words, that molecule could be inulin, is the one that represents the real and pure glomerular filtration rate in your kidneys.